we are going to discover incredible things that we never imagined.
The discovery of the Andromeda galaxy marked a turning point in our understanding of the universe, challenging our Earth-centered perspective and revealing the vastness of galaxies beyond our own Milky Way. However, recent findings from the James Webb Space Telescope have prompted a re-evaluation of what we thought we knew about Andromeda. What fresh insights has this advanced telescope brought to our understanding of Andromeda? And how has it reshaped our previous assumptions about this celestial neighbor? Let's explore this intriguing development, which involves the unexpected shutdown of the James Webb Telescope and the puzzling signals emanating from Andromeda. But before we delve into the revelations, let's establish some essential context. The James Webb Space Telescope, JWST, represents a significant leap forward in space exploration, specifically designed for infrared astronomy. Its cutting-edge instruments boast unparalleled resolution and sensitivity, allowing it to observe objects that were previously too distant, ancient, or faint for even the Hubble Space Telescope. This capability opens up new frontiers in various fields of astronomy and cosmology, from studying the earliest stars and galaxies to analyzing the atmospheres of potentially habitable exoplanets. Launched on December 25, 2021, aboard an Ariane 5 rocket from Kourou, French Guiana, the Webb telescope reached its destination in January 2022. A solar orbit near the Earth-Sun L2 Lagrange point, approximately 1.5 million kilometers, 930,000 miles, away from Earth. The world got its first glimpse of its capabilities when its inaugural image was released to the public on July 11, 2022. NASA spearheaded the design and development of the Webb telescope in collaboration with two key partners: the European Space Agency, ESA, and the Canadian Space Agency, CSA. The NASA Goddard Space Flight Center in Maryland oversaw the telescope's construction, while the Space Telescope Science Institute in Baltimore, located on the Homewood campus of Johns Hopkins University, manages its operations. Northrop Grumman served as the primary contractor for the project. With this foundation in place, let's delve into the unfolding saga of the James Webb Telescope and its remarkable discoveries in the enigmatic realms of the Andromeda Galaxy. The telescope pays homage to James E. Webb, who led NASA as administrator from 1961 to 1968 during the pioneering Mercury, Gemini, and Apollo programs. Its core component, Webb's primary mirror, comprises 18 hexagonal segments crafted from gold-plated beryllium, collectively forming a mirror spanning 6.5 meters, 21 feet in diameter. This dwarfs Hubble's 2.4 meter, 7 feet and 10 inches mirror, and grants Webb a light-gathering area roughly 6 times larger than its predecessor. Unlike Hubble, which observes light primarily in the near-ultraviolet and visible spectra, 0.1 to 0.8 micrometers, and near-infrared, 0.8 to 2.5 micrometers. Webb extends its vision across a broader range of frequencies. Maintaining precise observations demands extreme coldness, with the telescope's temperature held below 50 Kelvin, approximately minus 223 degrees Celsius or minus 370 degrees Fahrenheit, to prevent interference from the infrared emissions of the telescope itself. Shielded by a 5-layer sun shield, Webb is safeguarded against the warming effects of the Sun, Earth, and Moon. The monumental scale of Webb's 6.5-meter gold-plated mirror challenges our perceptions of the universe and our position within it. What does this mean for the future of space exploration? Can humanity evolve sufficiently to navigate the complexities of the Milky Way? Or are we destined for demise in this vast new frontier? Stay tuned as we delve deeper into these questions. The journey towards the James Webb Telescope, originally dubbed the Next Generation Space Telescope, commenced in 1996. Initial plans envisioned a launch by 2007 within a budget of $1 billion US, but the project encountered significant setbacks, including exorbitant cost escalations and delays. A substantial redesign in 2005 paved the way for construction, which concluded in 2016 after exhaustive testing, culminating in a total expenditure of $10 billion US. Here are the features of the James Webb Space Telescope presented in a more human-friendly way. Compared to the Hubble Space Telescope, the James Webb Space Telescope weighs about half as much. The primary mirror of Webb is truly impressive, crafted from gold-coated beryllium and spanning 6.5 meters, 21 feet, in diameter. It's actually made up of 18 separate hexagonal mirrors. This mirror provides a polished area of 26.3 square meters, 283 square feet. Some of this area, about 0.9 square meters, 9.7 square feet, is partially covered by support struts, leaving a total collecting area of 25.4 square meters, 273 square feet. This vast collecting area surpasses Hubble's capabilities. Hubble's mirror is only 2.4 meters, 7.9 feet in diameter, offering a collecting area of just 4.0 square meters, 43 square feet. To optimize its ability to detect infrared light, the mirror is coated with gold and then protected by a thin layer of glass for durability. While Webb is mainly designed for near-infrared astronomy, it can also observe orange and red visible light as well as the mid-infrared region, depending on the instrument being used. Its sensitivity is incredible, able to detect objects up to 100 times fainter than Hubble can, including objects from the early universe, reaching back to about 180 million years after the Big Bang. Why focus on the near to mid-infrared? Well, there are some good reasons. Objects that are very early and distant have their visible emissions shifted into the infrared, making infrared astronomy essential to observe them. Infrared light can penetrate dust clouds more easily than visible light, allowing Webb to see through these obstacles more effectively. Objects like debris disks and planets that are cooler emit most of their energy in the form of infrared light. However, studying these infrared emissions poses challenges both from the ground and with existing space telescopes like Hubble. Ground-based telescopes face obstacles because they have to peer through Earth's atmosphere, which blocks much of the infrared light. Even in areas where the atmosphere allows infrared light through, it's complicated by the presence of gases like water, carbon dioxide, and methane, which also exist in Earth's atmosphere, making analysis tricky. Current space telescopes like Hubble struggle to observe these specific infrared wavelengths because their mirrors aren't cool enough. Hubble's mirror remains at around 15 degrees C, causing the telescope to emit a lot of infrared radiation in those wavelengths. The James Webb Space Telescope, on the other hand, can observe objects within the solar system at certain angles and with specific rates of motion. This includes planets like Mars, Jupiter, Saturn, Uranus, Neptune, and even Pluto, along with their moons, as well as comets, asteroids, and minor planets beyond Mars's orbit. Webb's sensitivity in the near-infrared and mid-infrared ranges allows it to observe almost all known objects in the Kuiper Belt. Additionally, it's capable of observing unexpected events like supernovae and gamma-ray bursts within 48 hours of a decision to do so. Now, let's explore the mysteries of our own galaxy, the Milky Way. Just over a century ago, the Milky Way was often seen as a hazy band of light stretching across the night sky. Early astronomers lacked the technology to see individual stars within it, leading to varied beliefs about its nature, with some considering it the center of creation where the heavens and earth met. However, Galileo Galilei revolutionized our understanding of the Milky Way in the early 17th century with his telescope. His observations shattered the notion that it was simply a faint glow, revealing instead a vast collection of stars, planets, and other celestial bodies. Interestingly, our nearest galactic neighbor, the Andromeda galaxy, lies close to the Milky Way, hinting at the incredible scale of the cosmos. With estimates of around 100 billion galaxies in the observable universe, it's clear that the cosmos is far more expansive than we once imagined. with the number of stars within reach truly staggering. Galileo's observations dismantled the notion that the Milky Way occupied a central position in the universe, revealing it instead as a vast collection of stars dispersed throughout space. In 1750, English astronomer Thomas Wright proposed a groundbreaking idea in his work, an original theory or new hypothesis of the universe, which expanded our cosmic understanding even further. According to Wright, the Milky Way wasn't a random scattering of stars, but rather a flat layer of stars, with a portion of this structure encompassing our own solar system. While Wright's hypothesis represented progress in comprehending the Milky Way's layout, it was constrained by the limited observational tools available at the time, and astronomers regarded the Milky Way as the boundary of the universe. However, astronomical progress surged in the early 18th century. By the 1920s, Edwin Hubble, utilizing the 100-inch Hooker telescope at Mount Wilson Observatory, achieved a groundbreaking revelation. His observations, alongside the work of fellow astronomers, unveiled the Milky Way as just one among countless galaxies in the cosmos. Hubble's findings not only provided evidence for the universe's expansion, but also paved the way for the development of the Big Bang theory, fundamentally altering our understanding of cosmology. The James Webb Space Telescope represents yet another stride forward in our cosmic exploration. With its cutting-edge capabilities, Webb will enable astronomers to delve deeper into space, unraveling further the mysteries of the universe. From probing the origins of the first stars and galaxies to investigating potentially habitable exoplanets, Webb holds the promise of revolutionizing our cosmic comprehension and our position within it. As humanity pushes the frontiers of exploration, fundamental questions about our existence and our cosmic context endure. The James Webb Space Telescope, with its unparalleled abilities, stands poised to address these questions, shaping our cosmic understanding for generations to come. The revelation of distant nebulae as distinct galaxies, each housing billions of stars, represents a seismic shift in our cosmic perspective, fundamentally transforming our understanding of the universe. The Andromeda galaxy, also known as M31, has been a subject of astronomical fascination for centuries. Persian astronomer Abd al-Rahman al-Sufi in the 10th century depicted it as a small cloud in his star charts, dubbing it the Little Cloud, showcasing remarkable observational skills despite the absence of telescopic aids. It wasn't until 1612 that Simon Marius provided a more detailed account through telescopic observations, laying the groundwork for subsequent studies of this celestial behemoth. In 1764, the renowned French astronomer Charles Messier included Andromeda in his catalogue as M31, mistakenly crediting Simon Marius for its discovery, unaware of al-Sufi's earlier observations. However, each contribution added to the collective understanding of this enigmatic galaxy over nearly a century. A pivotal moment in unraveling the nature of the Andromeda galaxy came in 1864, courtesy of English astronomer William Huggins. His spectral analysis of Andromeda revealed distinctions from typical gaseous nebulae, offering new insights into its true identity as a vast cosmic structure rather than a mere cloud. With a mass estimated to be between 1 and 2 trillion times that of our Sun, Andromeda's colossal scale underscores its significance in the cosmic panorama. Through meticulous research spanning decades, scientists have unearthed captivating details about the origins and evolution of this ancient entity, believed to be around 10 billion years old. Andromeda's age hints at a rich history of formation and development, with one prevailing theory suggesting it arose from the merging of numerous smaller proto-galaxies over eons. This gradual process of galactic amalgamation, driven by the relentless tug of gravity, has sculpted the magnificent structure that captivates observers today. Recent studies have challenged long-standing assumptions regarding the size discrepancy between the Andromeda and Milky Way galaxies. While Andromeda's vastness has traditionally captured attention, new research has prompted scientists to re-evaluate its mass relative to our own galaxy. Despite these adjustments, Andromeda's considerable dimensions, boasting a diameter of roughly 220,000 light-years, remain widely acknowledged in astronomical circles. This shift in perspective highlights the intricate nature of gauging galaxy mass accurately. Galaxies represent complex systems comprising stars, gas, dust, and dark matter, with their distribution and motion exerting influence on overall mass. Achieving precise measurements necessitates advanced observational methods and meticulous analysis, a task facilitated by modern instrumentation and technology. One of the most intriguing aspects of the Andromeda Galaxy is its active galactic nucleus, AGN. The AGN constitutes a highly energetic region situated at the galaxy's core, emitting intense radiation across multiple wavelengths, from radio waves to X-rays. AGNs derive their energy from the presence of a supermassive black hole entrenched at the galactic center. These supermassive black holes epitomize regions of extraordinary density in space, where an immense mass is concentrated within a relatively minuscule volume. When astronomers scrutinize the active galactic nucleus utilizing sophisticated instruments like the Hubble Space Telescope, they discern a captivating phenomenon. The AGN manifests as having dual points of concentration, indicating the presence of two distinct regions emitting radiation more vigorously than their surroundings. The brighter focus represents the secondary concentration, slightly offset from the true galactic center. Nestled within this region lies the supermassive black hole, with its mass estimated to range between 1.1 and 2.3 multiplied by 10 to the power of 8 solar masses, equating to approximately 110 to 230 million times the mass of our Sun. Supermassive black holes, thought to be common at the centers of galaxies like our own Milky Way, play a pivotal role in shaping the evolution and dynamics of these cosmic giants. When matter, such as gases and stars, ventures too near the gravitational powerhouse of a supermassive black hole, an intriguing cosmic spectacle unfolds. This proximity triggers the formation of an accretion disk, a swirling vortex of material orbiting around the black hole. As this disk spirals inward, drawn inexorably by the black hole's immense gravity, it undergoes a monumental transformation. The intense gravitational forces involved heat up the materials within the disk to staggering temperatures, leading to the emission of a torrent of radiation spanning the electromagnetic spectrum. One of the most mesmerizing outcomes of this cosmic interplay can be witnessed at the heart of galaxies harboring active galactic nuclei, such as the Andromeda Galaxy. Here, astronomers focus their instruments on the AGN nestled within, scrutinizing its every detail with meticulous care. Within the vast expanse of stars and cosmic debris, they discern a peculiar anomaly, a luminous concentration near the central supermassive black hole. The origin of this radiant spectacle is truly awe-inspiring. At the core of the Andromeda Galaxy resides a gravitational behemoth, a supermassive black hole whose immense mass exerts an irresistible attraction on everything nearby. As stars orbit around this gravitational titan, they trace elliptical paths reminiscent of planets orbiting our own Sun. However, unlike the predictable orbits of planets in our solar system, the dance of stars around a supermassive black hole is a chaotic and unpredictable affair. Each encounter between a star and the black hole carries both danger and opportunity. Some stars narrowly avoid the event horizon, their paths altered but ultimately surviving the encounter. Others, however, venture too close and are consumed entirely by the voracious appetite of the black hole, contributing to the growing mass of the accretion disk. It is within this swirling maelstrom of cosmic matter that the Andromeda Galaxy's active galactic nucleus, AGN, draws its brilliance. As stars in their elliptical orbits approach the black hole, Reaching their closest point known as the perihelion, they experience the most potent gravitational forces, propelling them at their highest velocities. This proximity causes the stars to cluster more densely around the black hole, releasing energy in the form of radiation, including visible light and other forms of electromagnetic radiation. The heightened concentration of stars and the subsequent emission of radiation give rise to the luminous focal point that astronomers observe within the core of Andromeda's AGN. This distinctive feature yields valuable insights into the gravitational interplay between the supermassive black hole and its surrounding stellar environment. In addition to its AGN, the Andromeda galaxy boasts another fascinating attribute: an abundance of globular clusters. These clusters are dense collections of stars orbiting the galaxy's center, akin to satellites revolving around a planet. Andromeda is believed to host approximately 460 of these ancient and compact clusters, each containing hundreds of thousands to millions of stars that formed concurrently.